I still think that getting applause at the beginning is a bit weird because you haven't. But yeah. Yeah, that's good. I need some of those, and I've got a lot of coffee. So let's see what we get from those. So now this is about arrow analysis, but I want to first give you a bit of context of what it is and where we came to this. So we Kotliners like our nullability analysis, right? It's like no more null reference exceptions. They are all gone. And it's great because it's actually quite lightweight, right? You mark your values which might be null with a little question mark, and then you use question mark though. But on top of that is this kind of powerful static data flow analysis, right? Because when I see these and compare what you have to do in other languages, that you now, because you check that list is not null, somehow the compiler magically knows that within this block, you don't need your question mark dot anymore. So there is this analysis that the compiler is doing for you. So the question is, why stop there? I mean, we got rid of a terrible kind of exception, which is the null reference exception. But we have way more. I mean, the field is full of all these mines. So we can get index out of bounds exceptions because we are accessing the wrong index in a list. Or we can give a weird number to, like a person's age is -1, which doesn't make sense. So we have these illegal argument exceptions. So, why stop there? Why not do the same thing that we did with null reference exceptions? And yes, that's exactly what arrow analysis is. So we want your things to turn red and say, hey, no, you're wrong. You might get an index out of bounds exceptions. You maybe are initializing your values wrong. And this is all what arrow analysis is about. It's about extending, this idea of having small checks here and there, so your code becomes safe. So, well, that's like the fancy definition of arrow analysis. So it's like a static analyzer, and we do pre-post conditions and invariants. But let me a bit go part by part. So we build this as static analysis tools, and that means this is not something which happens at runtime. This is something which happens at compile time. If you really want to know how it works, is a compiler plugin built on top of arrow meta, so it's integrated on your build. It checks for pre and post conditions, which essentially means that you annotate your code with contracts, which are a bit more than just saying this is null or not null. And then the tool goes and checks this. And it's flow aware, which means that it takes the same ideas that I was showing before with nullability analysis. It understands how your code looks like, what kind of branches you are taking, and it uses this to give you, better information, right? So, I mean, I can always write a static analyzer which tells you every time you access a list, this might be wrong, but this is completely useless because you are just accessing them all the time. What you want to do is have something which says, this might be wrong, but actually, no, this is right. So you are good with that. Please go and check those 5 cases I'm telling you those might be wrong. Be careful with those. And that's what actually sets apart from what people usually call a linter. So a linter is more like something which checks for bad patterns, like you are using these 2 functions wrong, like when you get IntelliJ, the deprecated thing, and it's just crossed out, and then you click and replace with a new one. This isn't checking the flow of your code. This is just checking literally how your thing looks like. So let me introduce an example here, and it's in order to make my code short, that means that my example is more stupid than it needs to be. So I mean, you will write bigger things, of course, with arrow analysis, but just in this case, we are trying to build a kind of semaphore and kind of counter, and what we want to do is to always have a positive number when we increment. So in this case, if you want to check this, you can add a preconditions. You can also use requires, but we added this pre thing to make it more clear. It's like a precondition. It's something that the arguments must satisfy in order for this function to be correct. So this is telling you if you are calling increment, this should only be called with an x greater than 0. And I'm giving, well, and there is a nice readable thing so that you can show in error messages. So if you now go and write, val example equals increment -1, arrow analysis will tell you there is an error. This precondition value must be positive is not satisfied in this particular place. Why? Because you told me that the value has to be greater than 0, and I actually figured out that -1 is not greater than 0. That's not true. So this is essentially what it's doing. So, I mean, on a first thing, it looks like, well, this is only like checking the literal things. And actually, this is a bit how it all started, trying to just give better support for when you are writing literal things. But actually, as I was saying, arrow analysis is flow aware. So you can now write code like this, in which I'm calling increment. But look, I'm showing there in purple that I'm making a check saying, oh, is current greater than 1? And if so, I'm going to increment it. And now everything is fine, right? Because what we asked for is we need the argument of increment to be greater than 0. And we only call increment when current is greater than 1. So if something is greater than 1, assuming that we don't have overflows and all weird stuff, then it's also greater than 0. So this is fine. This is okay. So actually, arrow analysis won't tell you anything, which means your code is correct. And then, well, you can have then an else branch, and you can imagine this as actually being, oh, I'm calling increment with some current value, and then the compiler plugin telling you, oh, this might be wrong because you are not checking whether current is greater than 0 or not. And then that's when you go and change your code to have this if or whatever you want to do it. Like, doesn't matter. You can use if, when, or whatever. And then this is forcing you to check that whatever things should be true is actually true when you call your code. So that's how we envision using this. So you refine your code so that you know that everything that must hold holds in your code. Right, but there is still a problem with the code I showed you before. The problem is that if I do this, for example, I increment 1 and then increment, this is going to be rejected by arrow analysis. And that's because this small piece of code is only asking the developer for things, right? It's essentially asking, please, whatever value you give me, you have to promise me it's going to be greater than 0. But we need also promises in the, this has to be kind of a balanced relationship between the callee and the caller. You are not promising anything about the result. So, well, I mean, we know it's x plus 1, but we are not giving any information to the analysis to know what's happening with the result of this code. So for this, we need to add an extra thing which our analysis provides, which is like, oh, by the way, you can think about while I'm talking what kind of thing we can promise, right? I will show you how we promise, but think about what we can promise to make this whole thing be accepted. So I was saying, we need to now have a way to specify how the result value of a function can have some property. And this is by essentially using what we call a post condition. So it's kind of mimicking the syntax of the precondition and the requires, but about the result value. So you can just tag your result value, which is in this case is x plus 1, and say, oh, by the way, this result value satisfies that it's greater than 0. So it's because we have 2 lambdas, we have to have like parentheses and all of that. But ideas for nicer syntax are always welcome, by the way. But that's how what you can do. And now this whole thing is accepted, right? Because, well, increment needs its value to be greater than 0. And we know the first one is greater than 0. So the innermost call to increment is accepted. But now the result of the first increment has a promise attached to it. And this promise is that the resulting value will be greater than 0. So now we can call the outermost increment with this. So there is like this dance in which we ask something from the arguments, but now we promise something about the result, which then can be used to build larger and bigger analysis. And by the way, these post conditions are also checked. So you cannot lie to me with this, or not me, the tool, whatever. So if I say the result must be greater than 0, but then I go into a branch and I don't know, if the result is smaller than 0, I just return 0, and 0 is not strictly greater than 0, then this will tell you, I'm sorry, there is a branch in your code in which this condition fails. So you have a bigger error message in which it essentially says, fails to satisfy the post condition positive. So again, all the paths in your code are checked. So it's another example of this flow awareness I were mentioning. So it knows how the data flows in your code through ifs and whens and all of that, and tries to check that on every possible path in your program, all the things that you are promising, in this case that the result is going to be greater than 0, actually hold. And otherwise, it stops your compilation. So you might wondering, actually, where, it seems that there is a bit of magic here, right? Because I'm telling you, you are promising that the x is going to be greater than 0, and then somehow the tool is able to prove that the result is also greater than 0. But all what we know is that the result is x plus 1. So how does it know that if I take a positive number and add 1, the result is still positive? Well, that's you can see this as magic, but there is actually like a reasoning engine. So we are using something called an SMT solver. I will just go in the next slide about where the names comes from, but it's essentially a black box. I don't know. For me, it's really like a magic box. If you've never worked with this kind of thing, just use it, and then you tell it, oh, is it the case that if x is greater than 0 and the result is x plus 1, then the result is greater, let's say, than 1? And it says yes. So we just take its word and say, well, okay, then you can continue. You can, for example, change this to greater than 2, and then the SMT solver tells you, well, no, it's not the case. There is a case, which is in the case in which this is, for example, 0, in which it doesn't hold because the value is 0, 0 plus 1 is 1, and 1 is not greater than 2. So here is your counter example. By the way, we are working on using this information for better messages, but it's not there, so don't expect this from the tool yet. So as I was saying, we are using these SMT solvers. That's kind of a specialized software for automatic reasoning, and that's essentially a very fast tool which knows a lot about a very few things, usually about numbers and bit vectors and regular expression and things which are fast, the kind of things we know how to deal with fast. And the cool thing is that a lot of people have been working on this for decades. Like there is Set3, which is a project which is, I think, from Microsoft Research, which has like 15 years of people working on this. And some people wrote a bridge to all of them in Java, so we can just use it and leverage them. I'm just saying this because I think that's a tool everybody should know. Like, I don't know, it opens so many doors. The fact that you can suddenly say, oh, I don't know, if my discount is 10% and my thing is blah blah blah, will I ever get to the case in which I have to give money back to the customer? And this kind of tool telling you no means that, okay, I'm good, right? So anyway, error analysis is once you start doing this, you can keep doing more things. And I sort of promised implicitly that I will solve the problem with the index out of bound exception. So I rather do something like this. So here I have a small program. The program is essentially computing the average of a list of numbers, but this has a potential path. And the problem, and it can actually throw an exception if the list is empty. Because in that case, the size is going to be 0, we divide by 0, and again, we get an arithmetic exception. So one of the things we would like is for our analysis to say, look, don't divide by 0, because like the second argument to the division operator should be different than 0. So we taught our analysis to do this, but actually it's even nicer, because what you can say is, for example, the precondition is that the list is not empty. So you can just write it this way. So you can just ask as precondition, the list is not empty, and then because the list is not empty, and somehow it knows that the list not being empty means that the size is greater than 0, and then it knows that if it's greater than 0, it's not 0, then everything is fine. And again, all of this, I'm telling this, it feels like super complicated, but we just put all this stuff on the robot, and the robot says yes. But you might be wondering, okay, I'm telling about, like we taught our analysis to do this, so I'm sure that some of you are thinking, okay, are these people literally going around and writing a specialized code for every possibility, like division and list and all of that? But of course not. That would be very annoying. So how we do this is by actually having some syntax to add these preconditions and postconditions to libraries which are outside of our control, right? So we cannot really change the get function for a list. That's on the Kotlin standard library, but we want some things to happen, right? If you want to call get, it'd rather be the case that the index is greater than 0 and strictly smaller than the size. So you can write it down in something which we called a law for this function, but essentially it says, this is not for so this precondition is not actually for this function, is for the function you are calling. So this is a way in which you can get some kind of, essentially we do this because then you are writing Kotlin code instead of like weird XML, JSON files or whatever. So there is some amount of type checking going on and so on. And all of this is essentially the same thing that TypeScript folks are doing. So they have these definition files where they write types for a lot of JavaScript functions, but using annotations because we're in the JVM, right? So it's not a new idea. So currently we are annotating functions, and the good thing is the more functions we annotate, the better the analysis, because then that means more things can be detected. So we are almost done with the Kotlin standard library, which is small. That's good. We would like to annotate like the whole Java standard library, like all the collections and all the files. But yeah, that's way too large. Help is welcome. We are an open source project, so you have nothing to do this evening. That's a good thing. I'm happy to guide you into adding 100, 200 new laws. Anyway, and the third thing I mentioned in my introduction is that we also have something called invariants. And you can think of invariants and some of those conditions, like this thing is greater than 0 or the size is blah, blah, but which apply to a whole type. So you can have, for example, a class of positive numbers, and then you can say, well, for this class, it must be the case that value must be greater than 0. Which is great because it avoids repeating this thing over and over again, right? Imagine you always have like a positive number, like an age, and then you have to write all the time age greater than 0, age greater than 0. Well, just wrap it in a type and say this is a type of integers with this extra condition, the condition that this thing is greater than 0. Actually, and this is then assumed every time you use the type. For example, I have my positive number here, and I define an operator to add. Yeah, I have to So I have two positive numbers, and this is able to know, well, if you add two positive numbers, the result is also a positive number. Because, well, we attach all of these things, and the robot says yes. Good, and you don't, you don't need to have any problem with performance, because with this cool inline, I don't know, inline classes are they called? Yeah. You can just define these things. These are compile time checks, but actually they are erased in the runtime, so in the compiled code. So you are doing good things. You are making your domain be more strict while keeping all the performance. Good, and I know what you're thinking, and I'm just these are questions I always get. Like, how do you add it? There is a Gradle plugin. It's super easy. Is it gonna take more time to compile? Of course. I'm taking over a lot of your exceptions. I need a bit of time to do that. And we assume it's around 3%. I hope it was 3%, like 300% of your time, which is okay, right? If you are compiling one of these big Android projects, you are just going for coffee anyway. You go for coffee and lunch now. Okay. Does it integrate with IntelliJ? Yeah, not really. If you run it, and then the error messages appear, and you can go there, but it's not like IDE integration. But the JetBrains folks have promised that with the new version of the compiler, there will be ways to do it, to integrate more with the IDE. So, we are exploring this option once the API stabilizes. What I don't know is why you haven't asked whether this integrates with GitHub, because it's actually a cool thing we implement. I'm so proud that we've found this way. So if you add this thing to your build and this in GitHub, actually the errors show as part of your code, as comments. So then everybody knows it and can talk about things or comment or something like this. So we managed to integrate with something. That's one thing. Anyway, I talk about arrow analysis, but this is actually part of a larger family of projects, which is called Arrow. Just ask to the folks there who are doing the rest of the things. So it's like getting ideas for many places, from functional programming, formal methods, verification, and try to make the Kotlin ecosystem a bit better by building compiler plugins or libraries or whatever needs to be done. So, I think we use like Arrow Meta and KSP and a bunch of compiler stuff to do so. So just check it out. The worst things it may happen is that your compile times are now longer, but we are not touching your code. So there is literally no reason for you not to try this and make our issue tracker full of issues that I will be spending my nights on. So, well, thanks. I hope you enjoy the rest of your day.